Hello guys, welcome back. Yeah, gonna solve a string problem. That is, let's go graphically smallest equivalent string. Mm, it's a medium one, so like I just get it's wrong because yesterday is a string problem with the label version one. So I think the version two will come like tomorrow. Yeah. Now let's focus on this one. Statement given a yeah gives the statement gives us two string s1 and s2 and the string base string. That is, we say s1i and s2i are equivalent characters. Hmm. For example, if s in abc and cde, so we have okay, so each characters, yeah, you can see that s1 length and s2 length is the same. So we have this assumption like a equal to c and write b equal to c respectively. Okay. So equivalent characters follow the user's rules of any equivalence relation. As reflexivity that is equal to itself, but obviously symmetric. Like symmetric, like a equal to b, so b must be equal to a. Is understandable? Yeah. Transitivity, transitivity. A equal to b, then b equal to c implies that a equal to c. So like it's a bridge. Yeah, you know it's a bridge. If like a bridge a and b, then you have b and c. Then actually we can go from a to c, right? For example, given the square information from S1 ABC and S2 CD, okay, ACB, ACD, and AAB are equivalent string of like added. Let's see, uh, EED, and we got the S1 like ABC and S2 like CDE. So we can actually do the base string is actually do the transitions like E can transition, it can transit to C like this, right? And actually C can transit to A, it's gonna become this, and B can become C, like we got A, B, B as this, right? And A and AAB is the lexicographically smallest equivalent string of base string. That is because we have many solutions. So I guess the problem needs us to return the lexicographically lexicographically smallest equivalent string of base string by using these equivalencies information from S1 and S2. Okay, let's take a look at the constraints. That is 1000. Okay, 1000. That's good. Um, as that's lowered in the script letter. That's also good too. Okay. Processing. Okay. Um, Based on the equivalencies information in S1 and S2, we can group the character as AP. Let's see, AOKRS. Then we have got transitions from KIS, EI, and the character in each group are equivalent and short in lexicography order. The answer is back. Okay, let me see. You see that the parsers, right? Parser, you got each group. In group content B, that is M and B, and you can see that yeah, M is smallest. To A, we got A smaller. R, we got like K is the smallest. Lexicography order, lexicography order. K, next S to K and R. That is K2. So we got something like sorry, E. Yes, market. That is actually the explanation of the example in the solution is a spoil, is a hint. So okay, let me talk about solution here. That is, you have a list of transition, and for example, like this, draw like you can see like you have a character A, and you can transition to B. Uh, I don't draw the direction here because like B can track if symmetry, if the relation symmetry is if A can transform to B, it implies that B can transform to A. So I don't. It's like a direct graph, and B can transform to C. Yeah, for example, like that. You see this create a group that is from A, B. You can transform to A. That's right, and C can also transform to A too by doing this transformation C to B and B to A. That's right. What does it mean? This means that each group that is a a connected a connected component of graph of a graph can interchangeable interchangeable. What do I say? That's mean um, like for example, we have a graph with two components like this. Then all the member can transform to any character in the same component. For example, F can become E, E can become F, C can become A, B can become A, also A can become C, also respectively. We get um, so the solution here is try to find the group. X group here is a component in a graph of character. We got 26 character, lower English character, right? And the edge, what is the edge here? Edge here is use the S1 and S2 to construct the edge. Like you got A, you got it AC, just draw the edge from A to C. You got B, D, just draw an edge from B to D. Okay, so let's take the example one. You can see that you can got B. We have an edge to M, and A have to A to O, A to O, K to R, yeah, R to R. Okay, R to R. So we don't need to draw the edge here. And like R to K, K here, R to K, R to K, and E to I, E to I, E to I, and finally we got R to S, R to S. As you can see, we have three groups after explanation here. MP, right? AO, that is KRS, that is E and I, that is. So what next? What's next? After we find all the group, all the component inside a graph, what we're gonna do? Simply because in each component you can transform from a character to another character within the same component. And the best way to find the smallest lexicographic order character. For example, like this row, you got R, you got you gonna got the KRS, so the smaller EK, so all the character from this group can transform to K, right? So to find the lexicographically smallest equivalent, just find all the group that's been on the component inside this character graph. And in each group, find the smallest character and set it as the result. See? Let me write down something. Find on a connected component, connected component inside this characters graph, right? For each group, find the smallest lexicographic order, the order character. So then assign character same group. That is solution. Gotta do it. First of all, let's view the graph first. Yeah, vector character. No, I think we use in here. Iterations. gonna do some resize like 26 and better in 26. Gosh, no, like this. So we're gonna for to create the metric here. So we got u is s1I minus a, b is s1I. We convert it from character to order. A to sorry add to a to a and gonna push you push back b and also b push back u because in direct graph right we're gonna grab rising functions to to debug the fight on the component gonna got int yes uh, debug here caption on the variable u that is don't forget to uh, I mean, we need to find all the component. So we need to find vectors like group, groups, sick character. That is -1 if you want to know. So now we need to develop the file on the on the character. V is -1 we can develop to V. And but next we're gonna find the actually we need to find all the character inside this. Also we're gonna got a vector in vector try or something like that. Oops. You actually we don't need to do this. Can do something more better. Try because respect doing just debug try. So that is gonna create the vector sick and do something like if whoops I is not visited, so we can view that from this. Remember to assign to I want to remove this. How to make oh so actually forgot it. Do something like this, please. Try to one, whatever. So we gonna find the smallest character inside this. Okay, like smallest. You can decide to like 6, whatever. Why not? Okay. So the answers here, got the string answers, string answers, 4.1 to for each character inside the base string. We do something like answer plus groups C, got it. Mm-hmm. Function, Bible conversion. Actually, it's been the was near the write lambda function. No, no function. Point parameter. Uh-huh. So what wrong? No Bible conversions from lambda to oh uh okay, just write a function what outside here. I actually don't know how to fix it. I just want to save your time here. Actually, well, it's so actually it's so annoying. Tracing, tracing. This is simply just that. What now? Okay, you got a growth. So just passes into the dbf whatever gross. What net? Actually, we must minus a plus a. Okay, because we store, we store integer instead of got it. That is 100% in runtime in ON. Okay, more challenge or gonna get some more challenges from here, but let's so goodbye.